we introduce you to the upcoming demonstration on PFAS transport in porous media conducted in Laboratory of Transport Phenomena in Porous Media under the supervision of Christos Sakirov. In this demonstration, we aim to showcase the behavior and movement of PFAS compounds through porous media, providing valuable insights into their fate and transport in environmental systems. Through a series of carefully designed experiments, we exploit these results and implement into a model in a way to answer a question of how PFAS compounds interact with porous media, and also how various factors influence their migration. The demonstration will feature a custom setup that simulates a realistic porous media environment, allowing us to visualize and analyze PFAS transport using computational fluid dynamic techniques. Our findings will contribute to a better understanding of PFAS contamination in soil and groundwater, paving the way for effective remediation strategies. This research is conducted thanks to our partners from Denmark and Israel. So let's introduce you to the main part of this demo. Which is the purpose of the video, what methodology is followed, and which are the current case studies. The purpose of this study is to investigate the transport of PFAS in soil under various scenarios. Specifically, the study aims to understand how PFAS concentration change over time and how far they can migrate under different conditions. The methodology used in this study involves a combination of simulation and experiments. A 3D reconstructed solid field based on actual geological site of Korsør is utilized for the simulations. The mass transport equation under the unsaturated condition is solved to model the movement of PFAS within the soil. Experimental data is collected to obtain soil properties and retention model for accurate simulation. Case studies. Several scenarios are studied to examine the behavior of PFAS in soil. This is the scenario number 1. PFAS are in high concentration on the surface of the topsoil with subsequent rainfall. This scenario is designed to provide insights into the mechanism of PFAS transfer and help understand how different factors such as rainfall impact the distribution and movement of PFAS within the soil. Scenario number 2 will include adsorption of PFAS on the soil ground. This scenario is designed to provide the retardation factor depending on the adsorption rate and the adsorption of PFAS on solid grains of the soil. This geological site is considered a point of interest for the current research project. Many of you are aware of the fact that for many years Korsør served as a firefighting test site where firefighters would assess the effectiveness of foam in a real-life fire scenario. Unfortunately, this resulted in a significant amount of PFAS being dispersed into the ground. Given the scale of contamination, the remediation of PFAS in the soil has become of utmost importance. At the Korsør site, the geological representation takes the computational form depicted on the left-hand side, as developed by Eric Klint and his team. Our representation of the site is displayed on the right-hand side. In this simulation domain, we provide a less detailed but useful approximation of the actual site. The model depicts each soil layer as a distinct component with varying soil properties, allowing us to capture the relevant characteristics such as porosities and permeabilities. Additionally, on the top of the computational domain, there is a designated area represented as a rectangle which serves as a boundary condition. The whole geometry extends from zero level ground to minus 8.5 meters into the ground and covers an area 10 by 10 square meters. In the content of PFAS transport in soil, we deployed Richard's equation number 1. which is a partially differential equation that describes the flow of water through unsaturated porous media. This equation takes into account hydraulic conductivity, water content, and pressure head. Hp is the pressure head, capital C is the moisture capacity, Se is the effective saturation, and theta is the volumetric water fraction, which constitutes a relation that depends on hydraulic pressure. S capital is storage coefficient, K is the water hydraulic conductivity, D is the coordinate for vertical elevation. Here is considered Z. This equation is highly nonlinear because C capital, S, E, and K change with the hydraulic pressure and water content. Then in the next slide, you will see how they change according to Van Genuchten approximation. The velocity is described in equation number 2. It is a Darcy equation which includes gravitational effects. Ks is the permeability, Kr is the relative permeability, m is the dynamic viscosity, P is the pressure, Greek letter R is the density, and G the acceleration of gravity. In the equation number 3 is the PFAS transport equation. It's a balance equilibrium equation. Very briefly, this is the nonlinear terms included in Richard's equation, as mentioned before, that plays a crucial role in capturing the evolution of each component during the final assessment of the hydraulic pressure or capillary pressure. Having all the mathematical formulation in mind and the simulation domain that is created, we are moving to software implementation. We are focusing on scenario number 1. In this scenario, PFAS are highly concentrated on the surface of the topsoil and then starts raining. The following questions arise. How far does the PFAS transport over 5 hours of raining, and what is the distribution of PFAS concentration after 9 days from the occurrence? Let's solve our scenario. So let's now proceed with the demonstration where we will explore the functionality and capabilities of the subsurface module in Korsør multiphysics. Once the geometry is finalized, we move to subsurface module. Thank you, Scenarios, for giving me this opportunity to be part of this very interesting research, and of course, thank you all for watching this video.